Components of hydroelectric power plants. Different references have been taken from Devi Ghat Hydropower Plant, Nuwakot, Nepal. Dam. The dam is the most important component of a hydroelectric power plant. The dam is built on a large river that has an abundant quantity of water throughout the year. It should be built at a location where the height of the river is sufficient to get the maximum possible potential energy from water. Dams are individually unique structures, and dam construction represents the biggest structures and basic infrastructure in all countries. Water reservoir. The water reservoir is the place behind the dam where water is stored. The water in the reservoir is located higher than the rest of the dam's structure. The height of water in the reservoir decides how much potential energy the water possesses. The higher the height of the water, the more potential energy is. The high position of water in the reservoir also enables it to move downwards effortlessly. The height of water in the reservoir is higher than the natural height of water flowing in the river, so it is considered to have an altered equilibrium. This also helps to increase the overall potential energy of water, which helps ultimately produce more electricity in the power generation unit. Forebay. A forebay or head pond is the temporary water storage, regulating reservoir provided at the downstream end of the canal just at upstream of the penstock. When the turbine rejects the load, forebay acts as a storage reservoir, whereas it supplies water, a sort of regulating reservoir when load increases. In Devi Ghat HBS there is a forebay just upstream of penstock where water from downstream of Trishul is collected. A spillway has also been provided at the side of the forebay for the purpose of spilling the excess water. The water spilled is mixed into the river by dissipating its energy at stilling basin. For the purpose of flushing the sediments of forebay, 3 flushing gates are also provided. Intake or control gates. These are the gates built on the inside of the dam. The water from the reservoir is released and controlled through these gates. These are called inlet gates because water enters the power generation unit through these gates. When the control gates are open, the water flows due to gravity through the penstock and towards the turbines. The water flowing through the gates possesses potential as well as kinetic energy. The penstock. The penstock is the long pipe or the shaft that carries the water flowing from the reservoir towards the power generation unit, composed of the turbines and generator. The water in the penstock possesses kinetic energy due to its motion and potential energy due to its height. The total amount of power generated in the hydroelectric power plant depends on the height of the water reservoir and the amount of water flowing through the penstock. The amount of water flowing through the penstock is controlled by the control gates. Penstock in Devi at HBS is steel penstock that is partially buried and open in some locations. The length of the penstock pipe is 510 meters. No. Of penstock pipes equals 3, 1 for each unit. Water turbines. Water flowing from the penstock is allowed to enter the power generation unit, which houses the turbine and the generator. When water falls on the blades of the turbine, the kinetic and potential energy of water is converted into the rotational motion of the blades of the turbine. The rotating blades cause the shaft of the turbine to also rotate. The turbine shaft is enclosed inside the generator. In most hydroelectric power plants there is more than one power generation unit. There is a large difference in height between the level of the turbine and the level of water in the reservoir. This difference in height, also known as the head of water, decides the total amount of power that can be generated in the hydroelectric power plant. There are various types of water turbines such as Kaplan turbine, Francis turbine, Belton wheels, etc. The type of turbine used in the hydroelectric power plant depends on the height of the reservoir, quantity of water, and the total power generation capacity. Used water turbine, vertical axis Francis turbine. Speed of turbine, 333 revolutions per minute. Francis turbines are the most prominent reaction turbines, and they are the best fit to the medium head and flow conditions. The water enters these turbines radially, which means it enters perpendicular to the rotational axis. The water always flows inwards, towards the center, once it enters the turbine. The water exits the turbine axially, parallel to the rotating axis, after passing through the turbine. The flow is controlled in these turbines by wicket gates or guide vanes located upstream of the runner. The guiding vanes are oriented to provide the inlet angle in the runner that is required for a specified flow. This opening angle is changed to maintain the turbine's consistent speed under variable load conditions. A significant amount of hydraulic energy is converted into kinetic energy inside guide vanes. When the flow reaches the inlet of the runner, a part of the total pressure energy is converted into kinetic energy, and the rest of the energy is converted inside the runner blades, and the runner is connected to a shaft, which rotates the generator at a constant RPM to generate electricity. Generators. It is in the generator where the electricity is produced. The shaft of the water turbine rotates in the generator, which produces alternating current in the coils of the generator. It is the rotation of the shaft inside the generator that produces a magnetic field, which is converted into electricity by electromagnetic field induction. Hence, the rotation of the shaft of the turbine is crucial for the production of electricity, and this is achieved by the kinetic and potential energy of water. Thus, in hydroelectric power plants, the potential energy of water is converted into electricity. Powerhouse components. Middle dot cooling system. Middle dot ventilation system. Middle dot lubrication system. Middle dot drainage and dewatering system. Middle dot OHD crane, FEC. Middle dot air compressor system. Middle dot lighting system, emergency supply system. Middle dot station earthing, lightning protection. Middle dot fire detection, firefighting, and hydrant system, and middle dot safety tagging and safety interlocks. Cooling system. The cooling is realized by a closed system that circulates the cooling medium, water or oil, over the components and a heat exchanger where it releases the heat to secondary cooling water. The secondary cooling water is the same surface water that drives the turbines, and it causes problems with the fouling, scaling of those heat exchangers. As a result of this, the turbines need to be shut down regularly for heat exchangers to be cleaned. The economic impact due to loss of income for each day of turbine downtime is enormous, in addition to the budget that needs to be set aside for the workload of this.